And we are live. Hello everyone and welcome to the webinar on how to make hydrogen fuel cells cheaper and more efficient. My name is Arnes Biogradlia and I'm your host for this webinar. Hydrogen fuel cells are promising clean energy technology, but their high cost and low efficiency have hindered their widespread adoption. This webinar will provide a research perspective on how to address these issues. Our speaker today is Dr. Quentin Meyer, a leading expert in hydrogen fuel cells research. Dr. Quentin Meyer is a postdoctoral research associate and fuel cell cluster leader at the University of New South Wales in Sydney, Australia. He will discuss the following topics: general introduction of hydrogen fuel cells, low-cost catalysts, super-resolution imaging and modeling. Dr. Meyer will also share his key findings from two recent publications. This webinar is essential for anyone who wants to understand the latest research on hydrogen fuel cells and how to make them more affordable and efficient. Just a little bit of housekeeping before we get started. If you have any questions during this presentation, please type them in your live chats or send directly to info@energynews.biz. And now, without any further ado, we will turn our time over to Dr. Quentin Meyer. Quentin, please take the stage. Could you just turn on your microphone?
Can you hear me now?
Yes.
Let's give me one moment. Sorry. Just trying to go back in the slides. There you go. So hi, everyone. So my name is Quentin, and today I'm going to give you a talk on how to make hydrogen fuel cells cheaper and more efficient, looking at it from research perspective over the work I've been doing over the last year and a half. So first, the group I work on is called the Nanochemistry Lab, where basically we work on water electrolyzers, hydrogen storage, and hydrogen fuel cells. And we work all across different aspects of material discovery, so catalyst synthesis, with single atom catalyst, a lot of modeling and prediction, and we do characterization using operando methods. And finally, we have an aspect on commercialization with techno-economical analysis, cell and stack prototyping, and spin-out company. And the group is led currently by Professor Chuan Zhao, and we are part of two ARC Center of Excellence, the ARC Industrial Transformation Training Center for the Global Hydrogen Economy, and the ARC Center of Excellence for Green and Chemical Transformation of Carbon Dioxide. And my main area of research is hydrogen fuel cells, when we look at low-cost platinum catalysts, platinum-free catalysts, which is what I'm going to talk about today, and gas-fusion electrode, which is also a topic I'll get on today. So a few words about me. So I graduated from UCL with a PhD in 2015, with receiving an award from Research Excellence in 2017. I worked for 2 years as a postdoc from 2015 to 2017. After that, I moved to Australia, when initially I did offer some training for startups on fuel cells and lithium batteries. After that, I moved to UNSW, where I've been now. Well, what I've been doing is setting up a hydrogen lab and leading fuel cell research from catalyst to systems. And I was awarded the Young Chemist Award in 2021 from the Economic Division of the Royal Australian Chemical Institute. In the moment, I've got about 57 papers published, probably up to 60 by the end of the year, an exchange of 27. So this is where we are right now. We have a world full of fossil fuel, and we are trying to introduce more and more renewable and building a hydrogen society to drive us to a more sustainable and cleaner futures. And once you've produced all these hydrogens through, for instance, green hydrogen through electrolysis, some solar panels and wind turbines, you want to use it in something. And hydrogen fuel cells, which is hydrogen, oxygen, electricity, and water, are a crucial component of this economy. So first part is what's actually a fuel cell. So fuel cell is an electrical devices when you have a cathode and an anode, and on the anode side you apply hydrogen, which splits into protons and electrons, and on the cathode side your protons go across the membrane and they react with some oxygen and some electrons and they form water. And this is a very cool schematic of how the structure looks like. You've got a gas diffusion medium called GDL or MPL, the catalyst layer, naphthalene membrane, and you have this structure on both sides. So through this talk, I've got a lot of drawings because for me, it's important to try to do some rough drawings of whatever you're talking about in terms of research to understand it. So how do you actually make a fuel cell? Well, typically, you would start with some carbon paper, which is done like way before fuel cell is made in some fact by pyrolyzing some cellulose paper. After that, you want to make it hydrophobic because fuel cells produce a lot of water. You want to remove it, so you coat it with some PTFE or Teflon material. After that, you add a thin layer of carbon nanoparticles, which is called microporous layer. On top of that, you want to have your material that creates the reaction. So you put some catalyst, that's the material in yellow, and then you sandwich it on both sides, and you have a cathode, a membrane, an anode, and altogether that gives you hydrogen fuel cells. So now that we know what it is, let's look more into how much they cost and how we can make them cheaper. So the problem of hydrogen fuel cells is currently they are a very expensive product. And the reason they're so expensive is they rely on platinum catalysts for both chemical reactions. And platinum is one of the most expensive metals on Earth. So the figure on the left side is actually a prediction of the cost. Assuming that all the prices on the top side have been brought to minimum, you end up with a catalyst accounting for half the price of the product. When you look at the price of platinum and iron ore, these kind of things start to make a lot of sense. Platinum is somewhere between $25,000 and $100,000 per kilogram. Iron ore is a million times cheaper. So that's where we are. Platinum is too expensive to be scalable. It's also a very scarce resource. So if we were to move for a full fuel cell hydrogen economy, there wouldn't be enough platinum. So there are two ways to work on this. First one is lower the amount of platinum. And the other way, which is what I'm working on, is replacing platinum with iron-based alternative, because iron has some good activity for reducing oxygen. It's very promising, but it comes with a lot of very unique challenges. That's what I'm going to discuss today. So this is how we look at it. Hydrogen fuel cells use scarce and costly platinum-based catalysts on both sides. These catalysts have promising activity in liquid cells. When you put them in a fuel cell, it becomes a lot more challenging. And it's very important to try and understand why it's challenging and what's happening in the real device. So this is the reaction that we're looking at, the oxygen reduction reaction. Sorry, 1 second, sorry. Oxygen reduction reaction in fuel cell. Sorry, trying to move back. Yeah, oxygen reaction face some challenges in fuel cell. So when you're looking at reaction in liquid electrolyte, it's basically a perfect environment. You've got an infinite proton source, you've got saturated with oxygen, and therefore you can easily produce water and no problem of water management because you're already in liquid. When you look at a fuel cell itself, it's a completely different problem. First thing you have is a solid electrolyte membrane with some ionomer creating extra proton conductivity, some water, but you're in a very dry environment. And what you need for the reaction to happen is oxygen, electrons, and protons at the same place at the same time. So this is called the triple phase boundary, which is the way the reaction happens. It's at the electrolyte, electrode, and gas interface. And depending on how well you design your fuel cell and your electrodes, you may have only 10% of your active sites, the materials in red, or 80% of the active sites produce reactions in reaction. And it's quite a challenge to have as many active sites as you want. So this is how you would start a study on fuel cell on catalyst. First, you deposit your catalyst into a liquid cell. You bubble it to saturate with oxygen, and you get these kind of curves. When you get the half-wave potential, that's a metric we look at to find out how good fuel cells are. You get 0.81 for your hydrogen carbon catalyst, which is the material I'm looking at, which is without platinum, and you get 0.84 for platinum. So quite a good start. And then you want to know what's happening in the fuel cell. The one thing you can notice here is we use 60 milligram of platinum and 600 of hydrogen carbon. So quite a difference here. And I'll get back onto this later. So as I was saying, in the fuel cell, it becomes very different environment. The reason it's so different is your hydrogen carbon catalyst is not quite as active as platinum. So you need to put a much higher volume. So platinum on carbon is the material you can see in here. Platinum are the small yellow particles. Carbon is the black particles over there. It has been optimized for about 2 decades. And what I mean by optimized is the way your ink is prepared to put your electrode has been spent a lot of efforts. The amount of ionomer, which is the material you can see in the circles here, has been very carefully optimized to get the best interaction. And typically, you get a loading between 0.2 and 0.4 milligrams per meter square, which is somewhere between 5 and 15 microns thick. This kind of environment, proton transport is very easy because you're dealing with something very small. Oxygen diffusion should be minimally granted. Electron transport is not a problem. And hopefully water management challenge happen way after the catalyst layer. When you look at our hydrogen carbon electrode, it's quite a different problem. So the first problem is that the way it's synthesized, it's typically done taking a metal organic framework on which you dope some iron, and then you carry on pyrolysis. And so how you pyrolyze it, typically material particles are going to stick together, create some large agglomerates. That's why the particles over there in this schematic are much larger than they are here. And not only you have large particles, but you need a much higher loading, so a lot more volume. And that gives you a lot of problems. Particles may not be very uniform in size because of how they're agglomerated. So you may have some very loosely ionomer interactions with your particle, with your active sites. As a result of this, because you put something very thick, you may end up with a very long pathway for your protons, electrons, and oxygen to the active sites. And you end up with something which is between 100 and 180 microns thick, which is 1 to 6 nanometers square. 100 microns is the size of the thickness of a human hair. And in chemistry and in most chemical synthesis, when you start to be able to see things with your own eyes, then you're going to have challenges and things are going to get quite complex. So what you want to do is monitor this challenge using physical and chemical methods to actually figure out what's happening. So this is what happens when we test my catalyst in a fuel cell. So on the left side, it's called a polarization curve. On the right side, it's on the right arrow, it's called power density. You get somewhere around 1.8 watts per square in oxygen with back pressure. For platinum, if you use a fully commercial cell, you probably get somewhere around 2.4. And our own catalyst, hydrogen carbon, gives us somewhere around 1.1 watts per meter square with back pressure and hydrogen oxygen. So that's a good start, but there is still a very large gap, about 700 milliwatts per meter square. And we know that we shouldn't have too much gas transfer problem because we apply a large back pressure. And so what's happening is there's probably some very large charge transfer driven gap. And we want to know why there is such a big difference. So first technique we're going to use is called X-ray imaging or X-ray tomography. And X-ray tomography is basically used by having an X-ray source, a small sample that we take one angle, then you rotate it, and you take another image, and then what you end up with is a full tomographic construction or full 3D image of your cell. And X-ray tomography can image full cell samples really well because lab X-ray has a resolution of 1 micron. Fuel cell features we're looking at are in the tens of hundreds of microns. So we get quite a nice image. This over there shows you, if you look at a gas exchange layer, you get excellent resolution. You can see very well carbon fibers, how it's bonded together with ionomer, with PTFE, and you can get quite an excellent picture. So now we scanned our hydrogen carbon catalyst and our platinum-based catalyst in a fuel cell, and we get two very different images. So on the left side, you've got in red the hydrogen carbon catalyst. On the right side, you've got platinum-based fuel cells. And the first difference is obviously there's a lot more iron hydrogen carbon catalyst. That's because it's not as active. So you end up with something around probably 100 microns thick. Platinum on carbon is probably around 10 microns thick. So that's the first very large difference. And because it's very thick, your hydrogen carbon, it will limit gas diffusion and water transport. We can also see here a very visible crack in the thickness of the catalyst layer. That's typically what you want to avoid because right here there will be no electrical contact. It's a perfect area for water to accumulate, and gas diffusion may be challenging across this area. If you look on the other hand on platinum on carbon, it's pretty much an ideal case. You only have cracks the other way in the thickness that allow gas to diffuse. They're very good for water transport. So two very different environments. Another thing you can actually see if you look closely, the surface of the hydrogen carbon catalyst layer is actually very rough. That's because of the way it's deposited. You can't avoid agglomerates. Whereas on the other hand, platinum-based catalyst has a very smooth surface. And this may be so rough that if you try to use commercial membranes from companies like Gore or other suppliers that are very, very thin in probably less than 10 microns, you may even create pinholes because you're pressing something very rough on something very, very smooth. That's things to consider. So now this is a physical approach of it. Now we want to do some electrochemical measurements. So what I've done is some impedance spectroscopy. Basically, you oscillate the current and you record the voltage response, and you do this across different amplitude, different frequencies, and what you get is called a Nyquist plot over here. So Nyquist plots are used a lot by chemists, but the problem they've got is they're quite hard to actually understand what's happening in a Nyquist plot. So what I'm going to be using is called the distribution of relaxation time, which is a new tool to analyze impedance measurement. Allows you to basically extract different peaks based on different processes. So in our case, as far as we're concerned, the first peak is for proton transport limitations. Second peak is linked with the reaction we're looking at, so oxygen reduction reaction. And finally, we've got gas diffusion limitations at much lower frequencies. So when we compare our enriched carbon and a platinum catalyst, so the curves overall look quite similar. Initially, you've got very large charge transfer, then some ohmic resistance, and then a small term in the middle at the very end. Look at the other catalyst, it's very much the same story. But the biggest difference is that look at the frequency at 10 Hertz. Here it's in the low part of the process, which means we're pretty much done with what's going on. Here it's detected at much higher frequencies, which means that there is a lot more detected at lower frequencies. What does it mean? It means something is slower. But from there, it's actually quite hard to know exactly what's slower. So we've used our DRT technique to get a better idea what's happening. And so what I've done is I've taken every single of these graphs, calculated the DRT, and then used a bit of MATLAB to interpolate the data. And this is what I got. So as I said, this is directly the same information contained in my impedance measurement. So proton transport, OR, and gas diffusion, platinum on carbon, something quite classic. When I look at my enriched carbon catalyst, it's somewhat similar, but there is a big shift towards lower frequency. So proton transport issue is one peak. Here it's two peaks. This peak is proton transport in the membrane. This peak is proton transport in the catalyst layer. That indicates that it's a much, much slower mechanism. Now, when we look at the reaction, we switch it, we went from a peak of about 50 Hertz to somewhere around 5 Hertz, which shows we have a much slower process. And again, gas diffusion, although it's not as impacted, seems to be going at a slower rate. So this approach is quite nice, and you can use it to access all sorts of catalysts in all sorts of devices. And we've done a lot of work over the last few years using DRT. We've been quite successful with collaborators across a range of systems. What we want to do here is we can really see that the two catalysts behave differently in devices and cause you different problems. Now, the problem of these catalysts is first, they don't behave the same way, but they're also not quite as stable. So the typical durability targets for fuel cells, for platinum, is somewhere between 5,000 and 20,000 hours. These and losing about 10 or 20% performance. These catalysts can lose between 30 and 80% performance after 100 hours in aggressive environments. What I mean by aggressive is standard conditions that you would run in a real vehicle. So what happens out of this is a lot of catalysts that typically make very high impact journals. They're published in Nature, in Science. They actually have quite bad stability. And as a result, they're a fascinating concept, but they don't really make it past scientific curiosities because they don't have the lifetime you want that is desired. But that's how you need research to progress. And it's quite challenging to understand why it's so severe. So the simplest way to capture this is imagining someone jumping off a cliff. First few seconds things are good, and then you fall very, very fast. So during lockdown, I was basically stuck at home like everybody else, so I did a nice review paper. This gives you a sense of how enriched catalysts lose performance over time. So this over there, the peak power density. So they are the record-breaking catalyst. And you can see they lose performance. So this one, 80% in 35 hours. This one, 51% in 8 hours. This one, 47% in 100 hours. This one, 40% in 100 hours. So overall, there's quite a sharp drop. And more worryingly, it's not just a sharp drop, it also happens at the beginning of life. What I mean by that is if you capture a polarization curve once, this is the power you get. You capture it immediately afterwards, you may have lost 10%. And in the first hour, you may have lost about 20%, 15 to 20% performance. So as a result, the metric we all use, peak power density, about performance, can be quite unreliable because the loss is so fast, which means you captured this probably as fast as you could to get to peak power and immediately capture it. And as well, this is rarely published in papers, how many times people have tried before they got the peak power they're reporting. And there as well, because it's so unstable, there is very limited analysis in fuel cells, with most groups, as say, citing papers from about 15 years ago. So the two main reasons the catalysts are unstable is you have what is called iron demethylation. So literally iron active sites leaching out because they're not physically stable. And the second problem is we use amorphous carbon, which is quite sensitive to corrosion. So as corrosion happens, you first lose some carbon, and then you would even lose your active sites because they just physically detach. And figuring out what's happening in real device will help you mitigate the problem. So best way to figure out what's happening is try to isolate it. So this is a stability of a catalyst over 60 hours. So as I was showing you earlier, this catalyst, you could say, oh, that's not very stable. It's actually very much middle range of stability for a cap. So perfect for our study. It's middle range compared to the other materials in the field. And what we've done is we basically try to freeze this stability by taking measurements all the way at different points as the cell degrades. And so we captured the state of the cell using polarization curve impedance and also cyclic voltammetry, which I'll get back to. But before we did that, we did a bit of physical characterization. So operando measurement, we tried to do operando measurement. What we did here is we scanned a catalyst layer at the beginning, and then we scan a catalyst layer after 60 hours of operation. The first thing we can see is the electrode is way thinner after 60 hours. That's one thing. Second one, it's also much smoother if you look at the surface. So when you have a carbon-based material and you lose a lot of thickness and it looks smoother, typically what this indicates is carbon corrosion. We carried out some more advanced characterization using XPS and Raman, and we've confirmed indeed we have carbon functional group and carbon corrosion taking on. So that's one step. The second part is we know we did some Xan's measurement, X-ray absorption near spectroscopy, and we see basically a shift towards higher values. What this indicates is we have a higher oxidation state, increase in iron oxidation state. And what we can propose is we have demethylation of iron, and then our iron that turns into agglomerates of iron oxide nanoparticles. And we confirm that with CEM, we were able to observe them. And we confirm the demethylation with ICP because we detect a slower mass of iron in after different stages of degradation. So that sort of confirms what I believe, but these are just physical measurements, not chemical measurements. And it's important to say that you could have a lot of changes here, but if the active sites used are only at the top, they may not be impacted by the corrosion. Same for the oxidation states. If they're not the one contributing to reaction, maybe it's not actually that important. So how do we figure that out? So first step, we did some polarization curves, and then we can basically correlate the active site retention or active site loss, which is proportional to the current density around 0.8 volt after ohmic correction. This is what we get. So very clear graph. At the beginning, we have 100% of active sites that are usable, and within 10 hours, we drop to 25%. This corresponds from here to here. And then the interesting thing is that while we don't lose active sites anymore, what actually seems to happen is we still lose about half the performance. So active sites remain, but performance keeps getting worse. So there's a slower mechanism that actually takes place, which has nothing to do with active site loss. So this is where our chemical measurement come in. What we carried out is some carbon corrosion characterization using cyclic voltammetry. So cyclic voltammetry is a technique when we saturate the cell with hydrogen on one side, on the anode side, and nitrogen on the cathode side. So hydrogen becomes a reference electrode, a pseudo reference electrode. Nitrogen is used for neutral environment, and we just sweep the voltage, and we see multiple peaks. So this peak around 0.8 volt is for iron oxide, iron 2 plus to iron 3 plus, and this peak around 0.6 volt is linked with carbon corrosion. And basically, this peak becomes much smaller over time. This peak's much larger. So we've deconvoluted them, doing a bit of data fitting to actually try to get the peak area. So this is sort of accurate, but probably there's still room for improvement. But this is overall the picture we get. We get a very quick loss of our iron and an increase of this functional group, quinone, hydroquinone, which are linked with carbon corrosion. So they're carbon oxygen groups that form as carbon corrodes. So what we can see is that we have a lot of loss of iron. And then after 10 hours of operation, the cell basically just slowly corrodes nearly in linear manner as we no longer seem to lose a lot of iron. And now let's look at this from in our fuel cell perspective. So these two techniques, polarization curve and cyclic voltammetry, problem they have is that they're captured very quickly and they don't quite give you the state of the cell as it's operating. Cyclic voltammetry in particular, when you run CV, you assume that you don't actually draw much of a current, so all the active sites that are present are reachable and there is no proton transport limitation, so you just capture what's there. Now, looking at impedance spectroscopy, we get a quite different picture. The important thing here is that this is at the beginning of life. We got quite a small Nyquist plot. The point around 10 Hertz is towards the bottom. And as we degrade the cell, there is quite a large change, much, much higher resistance. And also the point frequency around 10 Hertz is moving closer and closer to the middle of the semicircle. And that tells us right away the reaction is becoming slower. Now, Looking at it with DRT, we get quite a different picture. So again, this is exactly the same data. There's two different ways to analyze it. We have a proton transport in the membrane. It's present from the very beginning. Then the two split into proton transport in the ionomer, so in the catalyst layer, and in the membrane. Your OR initially becomes much bigger and then slowly shifts towards lower frequency. And gas diffusion seems to basically disappear, which is a bit confusing. So starting from the beginning, what's happening in the catalyst layer, and why do we have proton transport resistance in the ionomer? So there are two ways to look at it, and this gives us just ideas of what's happening, not the definite answer. First one is we have a lot of iron demethylation, and as ions saturate my ionomer, they will stop proton transport because they're just literally another ion that's stuck. The other reason is as the electrode is corroding on itself, the proton pathway becomes larger and longer and longer and longer, much slower. That would explain why we see such a large proton transport in the ionomer phenomena. Now, looking at our OR, again, there are multiple ways to look at it. So the first one is we have our particles basically is roughly some sort of hexagonal particles, and you have the active sites inside the particle and outside the particle. So maybe initially use up the active sites that are outside the particle, very easy to reach. That's why quite low resistance, quite a fast phenomena. And then as you degrade, you have to go deeper and deeper and deeper into particle. And that's how you end up with some much, much lower process happening at much lower frequency and gives you high resistance. The other way to look at it, and these two could be linked, that there is other theories that explain that you have highly active site, but very unstable. Just give me 1 second, sorry. Highly active, but extremely unstable material, active sites, that could be the ones over here. And then you have some much more thermodynamically less active sites. These could be these ones who basically you switch from one predominance to this one. And there's been a lot of characterization on this, confirming this, so we could very much be looking at both phenomena. Finally, the improving coefficient diffusion, that was one that has been puzzling me for a while. The simplest way to understand this is that as the electrode collapses, you end up with something much thinner, so gas diffusion is not a problem. However, you may also have a smaller and smaller pores. So I'm not completely certain the story is quite finished here. What's likely is that maybe carbon corrosion happening at gas diffusion limitation happening at much, much lower frequencies. But because the system was not very stable, it was difficult to do a very long measurement. Like this measurement lasts 3 minutes. If we wanted to look at much, much lower frequencies, we may need to measure for 1 hour, which was not possible given the rate of decay. But this is the picture we obtained. So now looking at the carbon mechanism in fuel cell. First part is we have iron demethylation and iron oxide nanoparticles formation. So initially, we have quite a good interaction. So ionomer very nicely wrapped around particle, some nice polarized C8 particle with a lot of red active sites. And first step is we have less active sites, we have some nanoparticles formation, but overall, the interaction with ionomer hasn't been that effective. Now, as we have carbon corrosion and ionomer methylation, things start to look way worse. By way worse, I mean the interaction with the ionomer that was initially very good becomes weaker and weaker. That's because literally you have less particle for it to attach to. Same time, you have a lot less active sites. You may generate more heat against liquid corrosion, so your ionomer is going to shrink simply because there is more heat, so it starts to dehydrate. And this is going to give you a lot of problems. This whole part is when you don't lose active sites, or you lose few active sites, but it becomes harder and harder to reach them. You can see from here we've only moved from 3 sites to 2 sites. Not a lot of changes, just a much more challenging phenomena. So in the first 10 hours, we lose active sites, and then we have carbon corrosion and demethylation that will reduce the catalyst layer utilization. What does it mean reducing it? It means the catalytic sites are still present, but because the cell is degrading, it becomes harder and harder and harder to reach these active sites. So this is merely an example using our own catalyst. And what I really want to encourage people who work in the field is carry out their own characterization. And we hope that with a lot of more electrochemical characterization, you can actually understand what's happening. These measurements were done pretty much as the cell is running. So you can get information within just a bit of processing, and you can get a very clear understanding what's happening for catalysts. And we're currently trying new catalysts, and we can see immediately what's happening using these 3 different techniques. Now I'm going to focus on a bit of a different challenge. So gas and water diffusion is quite challenging due to the electrode thickness. So in my case, what we had is we had a fuel cell that operates at low temperatures, so below 100 degrees, and it fuses water. So there is a very delicate balance between flooding and dehydration. The reason it's so delicate is that the ionomer, naphthalene, needs a certain amount of water to operate properly. However, if you don't remove this water that you produce by the cell, you're going to have flooding with gas diffusion problem. And if you remove too much water, if you're too efficient, you will dehydrate the cell, you'll have lower product conductivity, and you'll have new problems again. So interesting thing that was a bit the drive for this is that this kind of energy carbon catalyst layer, they suffer from water accumulation because they're very, very thick with some cracks. So what we wanted to have is a large-scale water and gas transport model to actually figure out what's happening and solve it. So this is basically a challenge, a very well-known problem. When you want to image something that is very large, you can't have a very high resolution. It's like imagining if you're taking an aerial view of a city from a drone, you try to zoom in, the resolution gets quite bad quite fast. So in our case, for our fuel cell, what we would usually do, we have a large image, and you would just take a small chunk of this image, and you would run a model on this small area. Or you would forget completely the model, the real figure, and make a lot of assumptions based on how the fuel cell should be, and you run a model on that. The problem with assumptions, as we know as scientists, sometimes they're not correct, so we don't really know. And the problem when you use a very small volume, that's the feedback you often get in industry. You get asked, well, that was all well and good, but what about this problem? How did you account for that? Did your material have all these properties? On my larger area, your properties are not correct. So we wanted to actually do something different when we try to image over a large area. So the technique we worked on, we developed it, we refined it, is called super resolution imaging. So what we've got on the top side is basically an X-ray image when you're moving through the thickness of a fuel cell. So each slide is basically a different part of the cell. So we scanned it with 4 micron resolution. And then we used AI, and we scanned a smaller area with about 700 nanometer resolution. This was done at Zeiss, the main X-ray manufacturer. We had this image here with low resolution, this image with a higher resolution. And then we use AI to basically improve the resolution of this entire image, taking this image, small portion of this one, and together combining the resolution. And as I'm going to replay the animation, you will see the improvement is extremely evident. Oh, sorry. I'm going to try to replay this. Sorry. There you go. So here you can barely see fibers. They just look like clusters. Here you can see every single fiber. Here it's very hard to tell when one material ends and begins. Here you can see exactly how the two materials interact with each other. And finally, you can see a membrane. Membrane here, it's quite hard to tell exactly the interface. Here it's extremely clear where the membrane is. So you get a lot of information from here. And now that you have all this much cleaner image, what would you do with it? So you use even more AI or machine learning. So this is an image basically just grayscale, so you can't actually do it, you can't do any modeling with it. So what we've done, we used AI basically to segment this image. So we scanned we identified manually on a few images, and then we have thousands of images, and we are able, using AI, to train the model, and then you can propagate to the entire domain. And you go from this image to this one. And this is how it actually looks like. So on the top side, you've got your real image, which is before super resolution imaging, quite noisy. You have this image here, the super resolved image, and then you have the AI segmentation. And the AI segmentation, we've now identified every single material. This is every single fiber, cluster of fibers separated from the background. This is the microprocess layer here that you can see over there. You've got some catalyst layer over there and a membrane. Same on both sides. So you've got a very high quality resolution segmentation. And that's what you get. So you start from here. You get clusters of fibers. You improve them. You improve their resolution, and then you're able to image them with CT, and you get quite a good view of it. Nothing is ever perfect. You're using AI, so you may have some bit of artifact, but overall we get an excellent sense of what's happening. And so now we take this image, and we want to run a model on what's happening. So this is what you would do. You would do Lattice-Boltzmann simulation, taking this as a 2D structure, and we were able to simulate water emerging off this area. which is what it's produced in the fuel. It's produced in the catalyst layer, but what we made the choice is simulate what's happening as it emerges at the catalyst layer. So what we've done is we run some Lattice-Boltzmann simulation using on a 16 centimeter on 6 millimeter square sample. And this was done on some of the world's most powerful supercomputers, powerful computer called Summit, a computer cluster, which is the 5th most powerful computer, and Australia's most powerful computer called GADI. And what we get with this kind of things is multiple things are going on. So I'm going to slow this down a bit. Initially, we have gas, we generate water, it's flowing on our surface. And here we have some gas channel. So gas flows here there is limited gas diffusion. So as I'm going to speed this up a bit, you can see extremely well water droplets are formed and they're just being detached and attached and they're moving from the surface. And in this area, which is blocked from gas diffusion, you have immediate flooding with water saturating right away there. And as well as you go into dead-ended is the mode commonly used in fuel cell operation to save fuel or to save hydrogen. You have right away immediate flooding of the cell saturation. So in practice, you may not have that right away because the fuel cell generate heats, so that may happen over time, flooding, but it will eventually happen because you produce water and it eventually has nowhere else to go. So, and then you purge the cell and you get back to normal conditions. And this kind of model, which we publish in Nature Communication, the possibilities are limitless with it. So in our case, we actually overlaid a flow field. We didn't actually have a flow field. We just overlaid it manually. You can try to start any flow field design you want. You can try to think, what if I made my flow field so that I wouldn't have these two discrepancies? So you can try that. You can overlay different design. You can overlay forms. You can overlay all sorts of material and get a good sense of what's happening. And from there, you can first try new flow fields. And you can also try gas diffusion material with different properties. You can say, what if I change my contact angle? What if I change my hydrophobicity? And all of this can be, what if I made holes? And all of this can be done directly in the model. And then we have capability in USW to actually implement and prototype the real samples. And currently, without telling you too much details, because we're still filing IP, we've made some slight changes to our real flow fields based on this kind of images, and we are able to improve performance by 60 to 70%, which is quite a large breakthrough. So in conclusion, we have non-processional catalysts, and they face structural electrical challenges in fuel cells. And the key of this is that it's not straightforward to replace material. Another thing I wanted to stress is look at the image on the left side of this. So this is basically an image when on the left side, on one side, you've got the CT image, so 3D image of a fuel cell. And on the right side, you've got some kind of mapping or impedance and some sort of fancy grid, which is a mapping data. So the giveaway from this is that when you do some imaging, or anyone that shows you any kind of image, the assumption is that the sample you're looking at represents the entire area. Often, and that's very much highlighted in here, you have different gradients. Your sample is not representative of the entire area. So one thing that's particularly important, developing a method so you know exactly what you're looking at. You take a sample from say a battery or fuel cell, you want to know what has happened to this area, at what rate it degraded, and then you can make a more relevant analysis. Otherwise, you're just picking samples at random and you assume that they're the same and you almost want to make them fit into the story that you have in mind. So it's very important to separate the two. And I've seen some very nice work recently when authors specifically aim for areas they're looking for. So that's extremely important for fuel cell research and imaging research in general. Now, the second case is we want to get some more. So back to my catalyst, they're not behaving the same as platinum. And the operando method gives us a better understanding of what's happening. So first they lose active sites, and it's followed by decay in catalyst hybridization. And the kind of ways to mitigate it, there are 3 different ways at the moment. And now some of it has done what we do, some of it is more of the field. First one is you make a better catalyst to have a higher active site accessibility, so more porous. This is potentially tempting. The side effect of this is if you haven't solved the degradation mechanism, you may end up with something that degrades even faster because you have more active sites, they're accessible, and they will die, all of them right away. We've seen some very nice papers in the field with a durability of 40 hours and the best catalyst, and the catalyst held the record for a few years of being the highest performance. The other way is to improve gas diffusion to active sites. You can tweak the property of your diffusion medium to improve gas diffusion and limit water management, water flooding. The third way is to accept you have a problem, that you may not be able to solve it right away. But you can make an ionomer or carbon support that's much more resistant. For instance, Nafion ionomer is quite sensitive to poisoning. What if you use something that is not as good as Nafion, maybe not slightly lower proton conductivity, but won't be impacted by iron leaching? But that may limit. The idea of this is to limit your loss at the first loss and then a flat line instead of a lower decay. And similarly, for carbon corrosion, there's been some interesting work that has emerged from groups in the US when the particle is coated with a thin layer of graphene. That enables you to create a protective layer for your carbon support. The issue with techniques like this is whether they're scalable or not. If they're not scalable, they remain an inspiring concept for researchers, but they may not become what industry is going to be using for a few decades. So this is what the research is at the moment. So I'd like to iterate our group, and at the moment, the group increased actually. I need to update this photo at some point. The group increased to nearly 25 people right now. And I'd like to introduce collaborators. We have the Mutuous group for multi-scale porous transport in porous system, which is Professor Armstrong and Most Tagami group in USW Engineering. We've got Virginia Tech University that gave us access, with the National Security Institute gave us access to the supercomputing resources. Our collaborators in UCL give us a hand with analysis. Zeiss was very kind to actually provide this data for us, which enabled us to run the model. And we're also funded by the Austrian government and Austrian Research Council. And finally, there's some of you on this call that are interested by doing PhDs. You're most welcome to contact me later on, and we can definitely discuss for doing PhDs and joining our group in UNSW. So finally, I'd like to thank you for listening to my talks. And if you have any questions, you can answer them. And you can also write to me directly by email at UNSW. And now I'll hand back to my host for more questions. Thank you very much.
Thank you, Dr. Meyer, for a very insightful presentation. And we will go ahead and take some questions. Just a reminder, you can send your questions to the live chat or to info@energynews.biz. And it looks like we have quite a few questions. Here's the first one. Can you provide an assessment of the current level of maturity of hydrogen fuel cell technology, and what are the key factors that contribute to its maturity or lack thereof?
So fuel cell technologies are very mature, but they're suffering from a chicken and egg problem. So I'm going to detail that in a bit more details. So fuel cell technologies have been put in cars for nearly 15 years. They work completely well. The cars work outstandingly, but the issue you face is there enough hydrogen to actually power my fuel cell? So you need a lot of development in hydrogen. Also, the other problem they face is while the technology works perfectly well, it's not quite affordable just yet. It doesn't quite compare. And it's not affordable for a very simple reason. It's scale economics. You don't make enough of them. They're not going to become affordable. Another problem with fuel cell has been finding the right market. So in the 2000s, which is about when I started working in the field, there was a lot of talk about fuel cell passenger vehicles. That turned out that batteries seemed an obvious better choice. Even if you think, okay, I don't want to recharge my car for that long, actually it's quite okay to recharge for half an hour. To stop for half an hour car, that's how much you would fuel anyway. So fuel cells seem to have moved now to much larger applications. So it's much more mature for trucks and higher power applications. And even cases we're looking at very large power, like a big field digger, that's when a battery is never going to work. That's where the technology is going, in my opinion. The product maturity is there is still a lot of research going on in catalysts, and there is a large gap between the catalyst research and the actual acceptance by the field. So there is a lot of work that will happen that will take probably a decade before you have much cheaper catalyst in fuel cells. So I hope I answered your question here. Thank you.
Thank you. In your opinion, which industries or sectors stand to benefit the most from the adoption of hydrogen fuel cells, considering their current state of development and efficiency?
So to me, that's just it's purely my own opinion. Trucks are the market that will benefit the most from fuel cell. In terms of refueling, it's a market that doesn't need convincing of every single person. So unlike passenger vehicles, if you own a fleet of trucks, you can replace them with hydrogen or even like if you have on-site when you use like bus or something, you know exactly the journey, that will benefit immediately from fuel cell. refueling, it has very quick refueling, that would work right away. And the other market is, as I was saying before, is on factory floors. If you have a system, you can replace them very quickly with diesel. You can replace them with fuel cells pretty much immediately. That's the two kind of markets. I've seen emergence of buses, of fuel cell buses, but I'm looking to see how well that gets off. But to me, the truck market is an ideal market because you know exactly the routes of your truck. You know, people know exactly when their trucks refuel. You know exactly your itinerary, so you know where you can put your refueling stations, and you can design your road for the trucks themselves. So that's where I see the first biggest market for fuel cells at the moment. Thank you.
What are some of the critical steps and innovations needed to make hydrogen fuel cells not only more efficient but also cost-effective for widespread adoption?
It all starts with the catalyst. That's what I was showing. The first step you need is a catalyst that is very cheap, and you want something that's very easy to make. One of the problems of the catalyst that I've been presenting, and a few people told me that over this year, is that they're made using pyrolysis. So you may produce CO2 as you make them. That's not ideal. So you want a system that's very clean, very simple, and you can make it extremely large scale. So that's what you want, something cheap and large scale. Then you make a catalyst, then you start looking at the system. So you want to make a fuel cell as simple as possible. Simple, I mean as cheap to assemble. If you make very cheap materials, but the assembly process is very complex, you won't get there. So you want to make them as simple as possible. And from there, so you've made your device, you want to build an operating system that's, again, as cheap and as simple as possible to use. If your fuel cell uses a very complex surrounding system, it's going to consume a lot of power. It will make it very complex and not very affordable. So you want to simplify basically the entire process. And I know companies at the moment are focusing on basically trying to reinvent fuel cells to make them as simple as possible, the entire structure. So it's very cheap and very scalable. That's where the research should be moving at the moment, is making them scalable and cheap and scalable through the entire system. And you may want to consider recycling and end of life and how you would recycle them in 10 years as well. So I hope that answered the question.
That sounds very good.
Yeah.
How can collaboration between governments, research institutions, and private industry play a role in advancing hydrogen fuel cell technology and ensuring its widespread adoption in various sectors?
So that's the million-dollar question. So first part of the answer is typically if you want to do fuel cell research at advanced scale, problem you have in fuel cells is that companies are often more advanced than research groups, simply because they have more resources and they have different interests. So if you want to work on fuel cell research, which is what I've been focusing for 15 years, you want to work very closely with an industrial partner to understand the problems they're looking at and what it's trying to solve. I often see papers in the field when a researcher, does a very nice study, but a problem that has been known for a decade by industry and probably has been solved. First part, you want to stay up to date and discuss like the industry, what is the challenge? How can I help you solve it? Instead of an academic saying, I've made discovery, can give me money. The other way is much more beneficial. And then you apply for funding with governments, or you explain your problem and you find some research grants which are linked with industry, and then you make the three of them work together. And there's a lot of government incentive for fuel cells. So I hope that covers it. But the most important part is academics need to understand the problems that needs to be solved before trying to solve a problem that doesn't exist.
Thank you. How can we ensure that the development and production of hydrogen fuel cells align with broader sustainability goals and avoid any unintended negative environmental or social impact?
So this is a question a little bit out of my expertise, but I'll do my best on this one. The first part regarding environmental impact, you can look at them so there are two of them. The first one when you produce the fuel cell, second one when you recycle it. So going to recycling, there's a lot of work at the moment to recycle platinum of the fuel cell, and that's progressing quite. There is progress. I've even heard of companies who basically, instead of saying you own the fuel cell and everything, you own the fuel cell, but the catalyst you don't own them because the company in 10 years is going to get them back to recycle them. Another problem regarding environmental impact that may have been what you were thinking about is fuel cell use PFSA materials, which there is a lot of debate whether they're sustainable or not. In my opinion, because they are very, very stable, so they may release in the environment. So in my opinion, this will be solved. I completely believe that at the time, in a few years, we'll find a replacement that won't have PFAS. The other problem of sustainable is, well, you produce the fuel cell, as I was touching on it, you want to produce it in a sustainable way. If you use a ridiculous amount of electricity in a factory that is not necessarily clean just to produce the fuel cell, and you assemble it using methods that are extremely energy intensive, they're not going to be sustainable. So you want to focus on it, the whole circle of operations, of how the fuel cell operates, as sustainable when you make it and when you recycle it. Thank you.
And the last question, what are the key challenges that need to be addressed in order to commercialize hydrogen fuel cells on a large scale?
Yeah, so hydrogen fuel cells have been commercialized small scale for a long time. The first challenge to me is identifying the market that should be for a fuel cell. So a lot of fuel cell companies, what they focus on is we're going to make stacks. So they make stacks, they do it really well, and only later they try to find out what's the market they're looking for. That was done a decade ago. Now things are changing. You want to design the fuel cell for the market you're looking for. That's the first part to make sure you can commercialize them. Second part, and I hope I'm still answering the question, is making them as affordable as you can. And with the two together, you'll find the right market and you'll hold on to it, but you need to design a fuel cell for the market you're looking for. For instance, if you're looking at a fuel cell that operates at low power or backup power applications, say data centers, you won't need the same amount of power, or even you may not need the same catalyst than a fuel cell that runs in a car that needs a very high power, huge acceleration. So these may be completely different, not just different system, but different operating system, but they could be completely different devices with different chemistries because they won't be used the same way. So again, is identify the market and build a device based on the market you want them to work. And I think that's what it's emerging, but it's still missing. Because fuel cell companies focus on making the stack and then selling it to different markets, which may not be the way to go.
It looks like we have covered all the questions. Quentin, is there anything else you would like to cover before we wrap up?
So just a small thing, as I said before, I work in a group of about 24, 25 researchers, and I think sometimes we've ended up recruiting people through these webinars. So if someone is interested in contacting me, contact me on LinkedIn or my email. I think you can easily find it online. Just don't hesitate to contact me for any questions. And if you're looking for more advanced research, to do more research, we welcome anyone who is interested to contact me directly. So that's pretty much all, but we welcome people who want to talk more. And even if you don't agree with me, you're more welcome to contact anyway, and we can have debates for hours. That's totally fine. That's perfect.
Yeah. Great. Thank you, Quentin, and thank you, everyone. We appreciate you being here today. Please be aware that energynews.biz will have a very active autumn when it comes to interviews and webinars. Stay tuned for the latest and greatest news on hydrogen market. Thanks again for joining us today, and we will see you in the next one.